Okay, well, thank you. And I'd like to also say thank you to Marius and all the other organisers for inviting me to this wonderful conference. And also for inadvertently helping me with trying to overcome my fear of heights by booking the workshop on the 27th floor. So I apologise for the curtains being shut, but I also think maybe it also helps with seeing the presentation. So yeah, so as you pointed out, I decided at last minute to change the title of the talk quite dramatically to Testing Quantum Gravity with a Single Quantum System, since I think this better explains the talk, what it's all about really. And from this new title, you can probably guess that this is work that's very much inspired by the recent proposal to test for quantum gravity by Sugata Bose and his collaborators, and Marletto and V, which obviously forms an important part of this workshop. And following Marius and Carl, I'm going to be referring to this as the B and V proposal throughout this talk. And I know that Marius and V spoke about it already on Monday in their talks, but since our work is heavily based on it, so I thought I should at least give a very, very brief introduction to this again, especially for those who may have missed Monday's session. But I promise I will be very, very brief. So this is a proposal for a tabletop test of quantum gravity that uses two microspheres, each in a superposition of two locations, interacting through gravity. So here these ones and the twos labelled as two different microspheres, and the L and the R's labelled as two different locations that each microsphere can be in. So I'm going to keep things simple and only consider the smallest possible distance between these microspheres. And I'm also going to assume that we can neglect the electromagnetic interactions between the microspheres compared to the gravitational ones. So then if we start in a product state, we'll find that quantum gravity necessarily entangles our state and entangles our two objects. And in the weak field limit of quantum gravity, this is due to a relative phase phi here, which is between these two states, which people were just discussing on the board. And we find that phi is proportional to the square of the mass of the microspheres and inversely proportional to this distance. And this is essentially just coming from the force between these two states, so the gravitational potential. And the reason I haven't got any other phases is because I've neglected all the other forces between them, because I've assumed that these distances are much larger, so the forces are much weaker. So then if we use a Stern-Gerlach experiment, this entanglement that's induced in the locations can be entirely switched into entanglement in just the spins, and then we can measure the entanglements using some simple spin correlations. However, if gravity is a classical theory, so if the gravitational field is classical valued, and there are lots of theories for this, then we would find that this remains a product state. And the reason for that is because a classical mediator can't entangle two quantum objects, as Vlatko explained on his talk on Monday. And so then any sign of entanglement in this experiment would be evidence for a quantum theory of gravity. Now, in order to measure this entanglement, you're going to need something like 10 to the minus 14 kilogram masses, an interaction time about 2 seconds, and a distance of 100 micrometers. So then you get this phase to be of order 1. And right now in current experiments, we can only create superpositions of masses 9 orders of magnitude smaller. So there's no doubt that this would be a big challenge. But in the community, there is a lot of optimism that a significant breakthrough will be made soon on generating such large superpositions, and that perhaps this test could be achievable within the next couple of decades, which when you think about it is absolutely remarkable, given that not that long ago we thought that a test of quantum gravity would be practically unreachable. So this pioneering proposal has shown how you can test quantum gravity using a bipartite quantum system. And as you can probably guess from the new title of the talk, what we wondered was whether you really need a bipartite quantum system or whether we could just get away with using one system. So the reason for that, I guess it's mainly just for our own curiosity, but also because perhaps it could help with the experimental feasibility, since now, rather than worrying about two quantum systems, you only have to worry about one. So this is different to what Vlatko spoke about on Monday, because although he used just a single mass in that experiment, it's still a bipartite quantum system, since he has both the location and the angular momentum. So he's still looking at the entanglement between these two properties. Whereas here, we're talking about a single quantum system with no subsystems. So of course, we can't use entanglement anymore as an indicator of quantum gravity, since this isn't defined anymore here. So we need a new indicator of quantum gravity. And rather than doing the usual thing of building you up and building you up to the end of the talk and telling you what this is, I thought I was going to spoil it all for you and tell you that what we think this new indicator is the creation of a non-Gaussian or negative Wigner function states of matter. Now, I wasn't sure how familiar everyone was going to be with non-Gaussian states and negative Wigner functions, so I'm going to first introduce these two concepts briefly and apologize for those who are very familiar with these things. And then later on, I'll talk about how we think these could be used to test for quantum gravity. Right, so I'm going to introduce non-Gaussian states through the field of continuous variable quantum information theory. So the way in which quantum information is normally taught in lectures is that quantum information is decoded in discrete variables, such that there's a fundamental quantum information bit called the Q bit. So if we had a spin system, we could label the spin down by a 0, the spin up by a 1, and then we have something analogous to a binary bit in classical information theory, except of course we have a superposition of these, and this is what defines our Q bit. But you can also encode quantum information in degrees of freedom with a continuous spectrum. So for example, we can encode quantum information in the position or the momentum of a single particle. And then what you have is the analog version of quantum information theory compared to the more conventional digital approach. And this analog version is actually a very active research field, and it has very promising results for certain information processing tasks. You can also use it as a way to apply quantum information theory to quantum field theory. So for example, if I took a scalar quantum field in a box, then my Hilbert space is a collection of infinite dimensional Fock spaces, of course, each described by annihilation and creation operators. And in my non-interacting system, I just, of course, have a Hamiltonian that's of a collection of quantum simple harmonic oscillators. So then for each oscillator, we can ascribe a position and momentum-like operator, just as we can do in normal quantum mechanics. And then we can encode our quantum information in the corresponding continuous variable states for these operators, just as we did with a single particle. So then we've encoded quantum information on this quantum phase space described by these quadrature operators for our quantum field. And rather than working with the density matrix, in this case, it's often, to describe a state, it's often more convenient to use a continuous variable phase space distribution, such as the Wigner function. So this is Wigner cropping up again. So he came up with his function in 1932. What he wanted was a way to describe quantum corrections to classical statistical mechanics, which of course relies on a probability distribution on classical phase space. And what he originally wanted was a probability distribution on quantum phase space that derives from Schrodinger's wave function. But we can do the same with the density matrix, and you can define the Wigner function as the inverse file map of the density matrix, which is given here for just a single mode, but you can easily extend this to many modes or even a continuum of modes. So then for every density matrix, we have a corresponding Wigner function that lives in our quantum phase space, which is an alternative way of describing a state of the system. So here's an example of a Wigner function on some quantum phase space. So rather than being a probability distribution, it turns out that this is a quasi-probability distribution, in that although it takes on real values and it sums to 1, it can also take on negative values. And then the states for which the Wigner function takes on negative values have no classical counterpart in classical statistical mechanics, of course, and so we refer to these as highly non-classical states. So it turns out that the only pure states that have positive Wigner functions everywhere are Gaussian states, whereas, of course, the only states then that have negative Wigner functions somewhere are non-Gaussian states. So these are highly non-classical states. And finally, coming to it, what I mean by a Gaussian state is one that has a Gaussian Wigner function. So we could write the Wigner function in this form for a single mode, where X contains our phase space variables, here are the means, and this is the covariance matrix. And this is an example of a Gaussian Wigner function. Of course, another way of defining a Gaussian state, as you can see here, is that it's fully characterized by the first and second moments of our quadratures, or equivalently in the full quantum field theory picture, by the 1 and 2 point correlation functions for our field. So just a quick reminder of some important Gaussian states. The vacuum is a Gaussian state. Coherent states, the most classical-like states, are Gaussian. Squeeze states, which are being used right now by LIGO to improve on gravitational wave detection using techniques of quantum metrology, which I'll come back to later in this talk. and also the thermal states. In contrast, some important examples of non-Gaussian states would be the Fock states, with n greater than 0, of course, and also cat states, which are superpositions of coherent states, but with different phases. So you can see here how the Wigner function can take on negative values compared to the Gaussian ones, indicating that these are highly non-classical states. So I just wanted to point out that an entangled state can be both Gaussian or non-Gaussian. And also, unlike entanglement, a single quantum system can be non-Gaussian, and that's, of course, why we're interested in it here. So this characterization of Gaussian and non-Gaussian states is actually incredibly important in continuous variable quantum information theory. So, for example, it turns out that universal quantum computation is only possible with non-Gaussian states or non-Gaussian operations. Whereas, in contrast, if you just have quantum Gaussian states and processes, then this can be efficiently simulated on just a classical computer. So you can see here now how non-Gaussianity can be an indicator of a purely quantum process, and that's essentially what we're going to be using to test for quantum theory of gravity. I'll come back to it. So, given the significance of Gaussian and non-Gaussian states in quantum information theory, it's important to understand what Hamiltonians can create such states, of course. And in fact, a Hamiltonian that's at most quadratic in annihilation and creation operators, or equivalently in your position and momentum-like operators, can only ever map a Gaussian state to a Gaussian state, because this is generating a Bogoliubov transformation, basically, if you want to understand it that way. So in contrast, then, any other Hamiltonian, one that's cubic or higher order in quantum operators, will necessarily induce non-Gaussianity in the state of the system. So, for example, if I took a Hamiltonian of this form, with A dagger and A, the creation and annihilation operators of some system A, and then I couple this to any operator of some system G. So this could be any operator, it doesn't have to be the annihilation and creation operator. Then if I took a Gaussian state for the reduced state of system A, I will necessarily find that this becomes a non-Gaussian state. And the only way to prevent that from happening is if I remove a hat from one of these operators. Right, so just go a little bit different, but I'll come back to how this matches with what I've spoken about. So if we consider a non-self-interacting real scalar quantum field, then the Hamiltonian density for that obviously takes this form. We just have the kinetic terms. So then if I expand my field in annihilation and creation operators, the Hamiltonian is, of course, quadratic in these operators. In fact, we don't just have this term, as we have a free quantum field. And therefore, Gaussianity is preserved by this free theory. And of course, this holds for any spin field. It doesn't have to be a scalar field. I just took that for simplicity. Because for whatever spin you have, you always just have the kinetic terms. It's always quadratic.
In field theory, a Gaussian state is Gaussian in each mode?
Good question. Yeah, I think you have to. I think you have to be Gaussian in each mode. I think that's true. Yes, because
and vice versa. So it's the same thing to be Gaussian in each mode or to be Gaussian. Yes.
Yep, I think so. Yep, that's right. It was one of the properties of Gaussianity is that if you take away any modes, then that still preserves Gaussianity. So it has to be like this. Yes. So then let's consider interacting this non-self-interacting quantum field with a classical entity, which I call G. Then we can only add terms of this sort of type to our Hamiltonian density, where we could have various derivatives of our field as well. So basically the important thing is that we just can only add terms that are as much as only up to quadratic order in our quantum non-self-interacting quantum fields. And then, of course, the Hamiltonian is still quadratic in these annihilation and creation operators. We've just changed the coupling constants, and therefore Gaussianity is still preserved by this process. If, however, we make this into a quantum entity, so we add a hat to this entity G, then now we have Hamiltonian terms that can induce non-Gaussianity. Right, so that's the claim, that if we take matter to be this non-self-interacting quantum field, then any production of non-Gaussianity in the state of the matter would be a signature of a quantum rather than classical interaction, and that's exactly what we're going to be using to test for quantum theory of gravity. So I thought it'd be helpful to explicitly show this in the gravitational context.
The rational clarification, these G's that you put, is this the same degree of freedom? Is this still field, or it's some other degree of freedom?
I don't think it has to be a field. But
As it could be any
I think it could
other
be
quantum
anything.
system.
Anything. Yeah. Any quantum system. Yes. Any entity.
What kind of an operator is it?
Any-
It's acting on the vacuum. I mean, is it some combination of creation and annihilation operators?
I don't think it has to be.
itself, or it has.
G mu mu.
What is it?
I will come to that, of course. Yes, that would be that is what I would do.
You assume that you can access this degree of freedom, or you trace out the of this degrees of freedom. that
I
you
would
described?
I trace out.
You trace out.
Yeah. So
And
that's
you,
if I do that.
you said then you can have non-Gaussianity
Yeah.
Mhm.
even by tracing out.
Yeah. So if I was to take this bit, what I'm doing here is tracing out, of course. So I'm tracing out the system G because I'm always just looking at the reduced system, and this is therefore a non-Gaussian state. I could, if you want, I can.
Yeah, but you trace out. I'm not. I believe you. I just don't.
I can show you a slide with lots of complicated mathematics if you want, but it is at the end. I got one spare if you want to see it.
I don't know why this is so strange for me. It seems like a very cheap way to get non-classical states. You have a Gaussian, you have a Hamiltonian Gaussian, a free. Then you interact with something which you have no control, and this all usually in experiment you all the time interact with something which you don't have a control. And suddenly you have a quantum real non-classical state.
Yeah, well, only if you couple like this. I mean, normally in experiments you assume that you're working with something like this, right? Because normally you assume that this is often, it's like maybe the environment, and so it's something very like
If you
classical.
have a nanomechanical oscillator, which is a Gaussian state,
Yeah.
and you have a light,
Yes.
and you don't look at the light, you usually don't get anything interesting, except you look at the light conditional then nanomechanical oscillator, and then you have a non-classical state. That's why it's so fascinating. You don't care about interaction.
No, because as long as it's like this, I mean, if you were to take that light to be approximately classical, then in some coherent states, which I don't know what they do in optomechanics, if they do that or not. But if you take it to be in a large coherent state, then you can approximately say this hat is removed, and then I have still a Gaussian process. So often in experiments, it might be a small non-Gaussianity that you see that you remove as an approximation. Yeah.
So I have the same question that I just love this thing. And you're saying that you're sure that when you trace out, you still have non-Gaussianity. So I guess
Yeah.
one thing is the following, is to say that if lambda is small,
Yes.
you will not see it, and if it's large, you would. But the other is, why do you see? Do you have an intuitive reason of why it stays there after tracing
Can I say
out?
something about the intuition? Here, it's still interacting, so it's not some light coming from an outer. It's your quantum system interacting with this G, which then interact paths.
Yeah, and then I have entangled state, and I
then-
trace out, and I get a mixed state. And that's what I don't understand.
Yeah. Yeah.
So does perhaps this rely on having a very precise knowledge about how this coupling works, about G itself? Every this kind of small perturbation would wash out. in
But
the
what-
rest?
But why are you saying that you get a mixed? Do you mean a maximally mixed state? But but if it was, but that doesn't mean it necessarily is Gaussian.
I don't say.
Yeah.
So that's why I'm not sure. It's just I'm surprised, but it could be still non-Gaussian.
No, I think well, I could we can discuss afterwards. I can show you the slide with some mathematics. Where was I? Yeah. So I thought so I've been quite abstract up until now. I thought now I'd look at the actual gravitational context. So here I'm considering how matter and gravity interact in general relativity. Of course, this is described by the matter action. And importantly, if I neglect all of interactions except for gravity, so I'm assuming that I'm working in the B and V sort of context where I'm working in a situation where all the other interactions can be ignored compared to gravity, then the matter action, of course, just contains the kinetic terms. So here it's just written, again, for a scalar field, just to keep things simple, but this applies to any type of spin field. Of course, it's quadratic in the matter fields, and therefore if I quantize my matter fields, but I leave my gravitational degrees of freedom classical, then I get this quadratic interaction term. I get a system that preserves, a theory that preserves Gaussianity, as we spoke about last couple of slides. If, however, we have a quantum theory of gravity, then there must be some quantum operator associated with gravity, and therefore Therefore, we have a theory that can induce non-Gaussianity in principle. So I thought this is perhaps maybe even more explicit in the weak field limits of quantum gravity. So here we split the metric up into a background and then a perturbation, which we quantize. And then the way in which matter and gravity interact in this case is described by this interaction Hamiltonian here, where T is the energy momentum operator for our matter. And since we're neglecting all other interactions, of course, we just have the kinetic term. So again, we have this cubic interaction term, something that can induce non-Gaussianity. Whereas in the classical theory, we remove the hats and we get something that's Gaussian. So you can also visualize this from some basic Feynman diagram of vertices. So here's just matter creating a graviton. This is already a cubic interaction. It's not Gaussian. Here in classical gravity, we take off the hat and we get quadratic. So here, just to hammer the message home, and perhaps it's a bit more relevant for what you were saying as well, because in effect, I'm tracing out the gravitational degrees of freedom here. So if we consider non-relativistic, so the Newtonian limits of gravity, which is perhaps most relevant for these sort of tabletop experiments anyway, then if we have a continuous mass distribution, rho, then my interaction Hamiltonian, the way in which matter and gravity interact, is described here, where here is the gravitational potential, which is sourced by a mass distribution. Now I quantize matter. Let's take it to be a scalar field for simplicity again. Then my quantum gravity Hamiltonian is higher than quadratic in field operators. And I can now substitute in my potential. So this is essentially getting rid of my gravitational degrees of freedom. And now I have a Hamiltonian that's quartic in the matter operators. So this will necessarily induce non-Gaussianity. In the classical gravity context, I just remove the hat from the potential. I get a quadratic Hamiltonian. So this is quantizing Newtonian gravity, but we could take the same. We get the same thing if we take the non-relativistic limit of weak quantum gravity. So here, in weak field quantum gravity, this is coming from this Feynman diagram here with a single graviton propagator. Take the non-relativistic limit, and we get this quartic interaction term. So I've got rid of the gravitational degrees of freedom.
I'm sorry.
Yeah.
Can you go back? When you perform this kind of approximation,
Yes.
going from the actual theory to an effective theory,
Yes.
You didn't really discuss. Maybe I missed it. I mean, when you quantize gravity, you have to do some gauge fixing, right? So you need to put a gauge fixing condition, something like that. And when you pass to the effective theory, it might be gauge dependent. So how can you demonstrate it? It is not the effective theory does not depend on the choice of the gauge present in your perturbative quantum gravity.
To be honest, I'm not sure I totally know the answer, but I'm not sure it makes a difference. Yeah, I don't know why it would make a...
In principle, it can make a difference. The question is, you need to demonstrate that it does not. That's what I'm saying.
Okay. So you're saying if you need to, obviously you need to gauge fix in the quantum case, I get that. So then if you take this limit to the non-relativistic theory, you have gauge freedom.
Precisely.
Yeah.
So this gauge fixing might, I mean, if you choose two different gauge fixing conditions, they might lead to two different effective theories.
I totally, yes. Yeah.
So in principle, so you want to pay attention, not to be dependent, not to be sensitive to this kind of.
I agree. Okay, well, I will look at this more carefully. I mean, I think that although you would get a different theory, I don't think you would get something that is, I don't think you'd ever get something, say, quadratic in the matter operators for quantum gravity. I don't see how a gauge fixing could ever.
I guess it will always be quadratic. I mean, it will be of this type generically, but maybe not the value of the coupling constant.
Yeah. Of course, yes, yeah. No, that's of course true. But I guess what I'm saying here is that I don't, like you, Marius would say, I don't care at this stage, because all I'm interested in is just a signature that can distinguish quantum gravity from classical gravity. And you're right that perhaps in a particular context, maybe this is too small to see. Perhaps I don't know. But at this stage, I'm not interested in that. But I'll come back to that later, when I come with the experiments.
So since people seem to be asking questions, I'll maybe I'll ask questions as well. So I'm a little bit employed, maybe in question marks, that in an actual experiment, how would you justify, like there could be some non-Gaussian interactions in the Hamiltonian due to purely classical effects, right? Not related to the gravity at all. and maybe these are very small, but you know, if you did an experiment and you saw this non-Gaussian thing, what would give you the right to then associate this to, say, or you know, some quantum gravity effect, as opposed to some stray field, you know, 2 laps away, stray.
Yeah, I mean, you're right. The point is that you have to design an experiment that is good enough to overcome these things. It's exactly the same with the BMV proposal. You know, you could have a stray field that entangles your 2 quantum objects. So you just have to assume that you can work in such a good enough way to ignore all these other effects. But I mean, I guess one thing though is here that because I'm only looking at a non-Gaussian process, I only have to worry about non-Gaussian noise, because Gaussian noise doesn't make any difference. So that's one thing that removes lots of noise. And then, yeah, you just have to worry about non-Gaussian noise.
I mean, I was just wondering if you had, like, for example, like in the LISA experiments, right? There's tons of other noises and things coming from other sources completely unrelated to gravitational wave. But the reason why they are to argue when they see this, like, oh, this is a gravitational wave, something else, is due to the form of this noise.
Well, that's also
so I was wondering if there's a similar argument in here why you can, if you know, why you would.
Yeah. Well, to be honest, I haven't looked into that in enough detail to tell you the true answer, but I'd imagine that would also be the case. It just depends how precise your experiment is. And I couldn't say right now, without looking at all these other effects, how easy that is to distinguish. But I mean, I guess I'll come back to this a little bit when I'd actually talk about the experiment we propose. And then, yeah, I'll talk about it a bit more then as well. Any more questions? Nope. Okay, so given that, well, my claim is at least that non-Gaussianity is a signature of quantum gravity, I'm now going to finally describe a test that is based on this and is using a single quantum system. So the single quantum system we've chosen is a Bose-Einstein condensate, which I'm sure you don't be minding, but I'm going to do it anyway. Is obviously the state of matter where identical bosons, in this case atoms, macroscopically occupy the ground state. And scientists have been creating such states of matter now for 25 years, so we're very experienced with these sort of systems. So what's happening as the atoms occupy the ground state, the de Broglie wavelengths begin to overlap, and eventually, in principle, they completely overlap, and then they have the same wave function. And so the entire wave function of the whole BC, the many-body wave function, is then just the product of these identical single-particle wave functions. Now, since we're working with identical bosons, though, it's often more convenient to work with a second quantization picture. So you can introduce a scalar quantum field for the atoms so that psi dagger creates an atom at some position r. But since our ground state we assume is macroscopically occupied, then we can approximate this as just a condensate wave function together with this associated annihilation operator. So then if I just took Newtonian gravity and I should say that, of course, gravity acts between all the atoms in the BEC, and we can take the Newtonian limits of quantum gravity. So I could just maybe say that I just quantize Newtonian gravity, or I can say I take the limits, whatever. Then going back to the few slides, what we have is, for quantum gravity, we have a chaotic interaction term that's in the annihilation creation operators of the condensate compared to this quadratic term. So we're only going to see non-Gaussianity in the quantum version. So in order to actually detect this non-Gaussianity, we've considered looking at a non-zero value of a fourth-order cumulant of a generalized quadrature. So a generalized quadrature is defined in this way, where at zero phase we just get the position operator, pi over 2 we get the momentum-like operator, and this is how the fourth-order cumulant is defined. And for those who are not so familiar with these, the first one is the mean, the second one is the variance, and then anything higher order than that is 0 for a Gaussian distribution. So we're looking at the fourth one, not the third one, because the third one can also be 0 for a non-Gaussian distribution if it's symmetric, which could be the case here. So we're looking at fourth. And just to say that this is kind of equivalent to looking at the 4-point correlation function of our entire BC field and asking if this is fully characterized by the 1- and 2-point correlation functions. That's what defines.
This is non-interacting BC. Like, it's just this. I mean, why do you use BC? It's not repeating a single particle experiment.
Yeah. Okay. There's a few reasons for using the BC. So one, which people keep asking for me before I come to it. No, I just say it now anyway. So one is because you can. There's a tool that people do in experiments which allows you to tune the interactions between the atoms so that you can effectively make these free systems. So that's one reason, because I can get rid of the electromagnetic interactions. And the other reason is just because I guess we want to look at a single quantum system. Well, I guess that is the same reason. Yeah, the main thing is to get rid of these electromagnetic.
Single particle, you don't have any interaction anyways. You just single particle and a single particle again.
If I had just had a single, you mean a single particle, just a single atom?
Yeah.
Yeah. So what's the question, sorry?
So why don't we use it a single?
Why we use a
Atom?
single atom? Oh, because
No, gravity.
Yeah, it's
It
not
doesn't
gravity.
gravitate with itself.
It'd be a gravity between the quarks and the electrons in
In a
between.
field, the piece of the field with the other piece of the field, or two atoms on the other. He said he cheated us because he
So
said
why this single particle?
he said a single
yeah, single
particle
system.
system to start with, but that
Yes.
was misleading because he's actually he's
No, no,
Probably it's kind of
confused. I'm totally confused.
properties of a single system without caring
single
about the
system.
bipartite.
It's a single quantum system because these are identical bosons all in the same state. So they're all, you can't distinguish between them.
It's still many.
Yeah, but then I take one single atom and the other single atom.
Sorry, I gave
Yeah,
the warning
so-
to the speaker, but I should give it more to the audience. We have 10 more minutes, including questions. So just you guys decide how you want to distribute it. Let's make a good use of our time.
Richard,
Yes.
can I speculate on what is the answer on Tesla's question? So we were just discussing it before. You have a parameter in your the notes you sent, and I was saying that you're seeing the Planck master,
Mhm.
and I
Yes.
think that's going to be the answer. He has to choose some experimental parameters to see this, and he needs a large mass to make it visible.
Let's. I'll show. Yeah. Okay. So just very briefly. So unbiased estimators are these cumulants of case statistics, which I'm just telling you this because you can then associate a quantum noise with each measurement. You get a signal-to-noise ratio for this measurement, where the noise here is just the quantum noise, so it's the one you can't get rid of. I'm not taking any of a noise at the moment, so it's the basic one. Now we're going to use. Now, obviously, you want this signal-to-noise ratio to be as large as possible. And in order to do that, we're going to exploit some techniques from quantum metrology. And this basically just means that you need your initial quantum state to be as highly quantum as possible. And this is actually pretty much just what they use in the B&V proposal. This is another way of looking at that test, is that they use effectively noon states. And these are the most non-classical states you can get. And this is one of the reasons why the signal is so massive in that experiment. So rather than using noon states, we've considered using squeezed and cat states in this case. And then you get the best scaling you can for the signal-to-noise ratio. You get a quadratic scaling in the number of atoms. And so here, of course, and of course, if you had a classical state, you don't get such a good scaling, so you get a huge loss of performance. And just to say, of course, this is a Gaussian state. So here I am looking at the production of non-Gaussianity, whereas a cat state is more complicated because a cat state is non-Gaussian to start with. So here I'd be looking at the change in non-Gaussianity as a signature of quantum gravity. So just as an example, you could take a spherical BC, which people can do in the lab, and take that to have mass m, radius r, take these initial squeeze or cat states. Then my signal-to-noise ratio, interestingly, looks the same as the B and V phase. The only difference being that I replace this distance between the microspheres to be the radius of the BC, which kind of makes sense if you think about it. The only other difference is that I've introduced this curly m, which is just the number of repetitions of the experiment. So for obviously the more times you repeat, the lower your noise, the higher your signal-to-noise ratio. For just one measurement, we get pretty much the same looking thing. So this coming back to what you were saying then, Shazlev. So this, if I just use one atom, of course, this goes away. The mass is nothing, so I can't test it with this. This is why I take a BC. And I claim it's a single quantum system because it's a single mode. It's like a single mode of a harmonic oscillator. You can't distinguish these particles. That's why I see it as a single quantum system. You can't get entanglement in the system. That's a whole way of thinking about it. So, of course, because of this, we're going to have to use similar parameters to the B and V proposal. So, for example, if we took a radius of 100 micrometers, which is pretty standard for a BC, this interaction time to be 2 seconds again. And actually, here I'm going to use the fact that we can, of course, repeat the experiment many times, which I don't think they initially did in the B and V proposal. And we can use that to reduce the mass that we need to put into this quantum state. So here, perhaps we could get to 10 to the minus 15 kilograms or smaller, which means about 10 to the 9 atoms. Now, getting 10 to the 9 atoms is probably be achievable in the short term, given what previous studies have managed to do. But of course, what's important is that these previous studies, they didn't generate highly quantum states of a BC. And that's what we need to do here. That's what a big challenge would be. It's just as in the B and V proposal, we couldn't create these highly quantum states right now. This is one of the experimental challenges. So another experimental challenge is to make sure that all of the interactions in your system are smaller than gravity, again, just as in the B and V proposal. And in the BC, this means making sure that all the electromagnetic interactions between the atoms are smaller than the gravitational interactions in your entire system. So in a BC, of course, the atoms are neutral, and they're also quite far apart, but there still will be some weak electromagnetic interactions. But due to a phenomenon called Feshbach resonances, it turns out that these interactions are tunable by applying a magnetic field to your BC. So this is what they do in experiments. And if you vary the magnetic field strength, you can vary this effective interaction strength between the atoms. And in fact, you can, in principle, turn these off completely. So there's some value that you can turn it off with the magnetic fields. So then the experimental challenge here is to make sure that once you set your magnetic field to that value, then any fluctuations in your magnetic field are small enough such that the electromagnetic interactions always stay below the gravitational ones. So in principle, perhaps we could also use this phenomena also to create the initial quantum states. So just as you can reduce the interaction strength, you can also increase it using these magnetic fields. And if you ramped up the interaction strength and then turned it off, you can create cat states of your BC in principle. Alternatively, if you wanted a squeeze state, then you could use a spinor BC by putting large classical condensates into plus and minus 1 hyperfine levels, let them interact, and then we get this squeeze state that we desire. Right, just thought it'd be useful to give a quick comparison between the gold standard test of quantum gravity compared to this sketch of an experiment we're thinking of. So of course the biggest difference is that this is, as I claim, is a single quantum system, which just relies on the gravitational self-interactions of the BC. Of course the indicators are different, the strength of the signal, they look kind of similar, both need highly quantum initial states. Interestingly, in the B and V proposal, you have a superposition of locations, which is perhaps what you'd expect for a test of quantum gravity, but that's not what we have here. We just have a single BC in a single location. The experimental system is, of course, different. The measurement schemes are going to be slightly different, though they will be quite similar as well. Both need to suppress electromagnetic interactions, and interestingly, both need this high control of an external magnetic field, since in the B and V proposal, you need a really strong magnetic field to drive these massive quantum states through your Stern-Gerlach experiment. So you also need control there. I also wanted to just say, to point out an interesting difference between the two indicators. So actually, it turns out that a classical interaction can create entanglement if that interaction involves a direct interaction of the two objects. So this would occur if the interaction is non-local, but we know that gravity is local, at least at the scales we're testing at, or if the wave functions of the two objects overlap, so that there is some probability that some parts of the objects will be in the same location at the same time. So this latter effect has an electromagnetic analog, and it's called tunneling, and you get it in double well BCs, where your electromagnetic potential is assumed to be classical, and then you get entanglement between the two wells of your BC. So you can see it in this gravitational context, when you take the Newtonian limits of classical gravity, then in principle you have terms such as these in your Hamiltonian, which are beam-splitting-like terms, so that if either object is in a quantum state, it will necessarily create entanglement between your two objects. Now, for something like the B and V proposal, I'd imagine that you can probably come up with ideas. Well, it's probably not difficult to rule out both of these scenarios. I suspect so anyway. But I still think it's quite interesting that if we look at these terms, these are quadratic terms. So although classical gravity, a direct classical interaction can create entanglement still, it can't create non-Gaussianity. But I don't want to give the impression that I think the non-Gaussianity indicator to be more general than the entanglement indicator. I actually think the non-Gaussianity one is perhaps it's harder to understand its full generality because it's based on a form of a Hamiltonian, whereas entanglement is based on a sort of nice, simple idea of how a classical mediator can't entangle two quantum objects. Do I have any time left?
How much time do you need?
None, because I've got the summary, but...
Okay. I think you deserve the time to do it.
So just to summarize here, so I've tried to introduce a new indicator of quantum gravity, which is non-Gaussianity. So this can be applied to a single system, as I've shown, but of course there's nothing stopping it being applied to a multipartite system, since non-Gaussianity is a single and multipartite process. I was wondering if also maybe interesting to look at combining these indicators, so you're looking at a non-Gaussian entangled system, is then perhaps you can rule out these direct classical interaction entanglement processes. So I've looked at a single BC, but again, this could be applied to any system in principle, so it's an optomechanical system, I think. And I wanted to touch on something that I think Vlatko also touched on in his talk on Monday, which is that this way of testing for a quantum theory of gravity is perhaps equivalent to asking whether gravity can perform universal quantum computation or not. So there's a sort of link with quantum information theory there. Just some quick things on things perhaps still to do, which Marius touched on before, which was that it'd be nice to have a better understanding of the role of the Planck mass in this process, similar to what Marius and Carla did with the B&V proposal. And perhaps it'd be nice to give an example of this non-Gaussianity process also with a quantum theory of gravity, such as loop quantum gravity, but that's a bit speculative. Right, okay, that's it. Thank you very much.
We did have quite some questions during the talk. Let's have a couple more now and then move to, well, I guess we have an appointment.
We should take a small break of 5 minutes because I want to test some technical things.
So do we have time for 2 questions?
Yes.
Okay, so Czaslaw and Marco.
So it's still
And then
clarification. So is it true that that's gravitational interaction between the atoms constituted B and C?
Yes.
But the advantage over, I understand, an entanglement experiment is that I could witness a quantum gravity effect by selecting one atom on time and measuring some property of the single atom, never about correlations. So I take another, after a while, one, like from the BC I take single
Yes.
atoms. Would this effect be there, or I have to take sometimes more and look at the
Yeah,
correlations?
no, I don't think you could just do it with one. You have to look at correlations. So it's, if I go back to,
Is then single, I mean, this I understand.
Don't take single too heavily.
No, that, I really,
In some sense it is.
understand.
but I mean, just to extract one atom.
And many statistics taking
Yes,
by atom.
yes.
By atom, yeah.
I don't think you could, I think it would have to be, yes, correlate. I don't, in terms of talking about atoms, I'm not sure if that's the correct thing to be talking about here.
You agree on the substance, you only disagree on the names.
That's probably true, yes.
That's what I'm saying.
It's not a
Don't
single
discuss
system.
about names.
Okay,
Um,
He
all right.
doesn't want to say single.
You don't, yeah, you don't,
No, I mean, like with the Marco say, oh, these 2 particles are single system.
BC people like to say it's a single.
It's I don't understand.
oh yes, no, that's true. So I think, yes, okay, I understand now, yes.
Not single particles. I mean, they're composite of many atoms.
So
Each
No, yes, single is probably a bad word, because, so I don't mean,
So
I don't think there is a word for it actually in quantum mechanics. Like you have a bipartite system, and I'm talking about like a single part system. So it's something that I only have one state for. I can't write my BC as anything other than, you know,
But
the
in the end,
kets in
this
this
boils
case.
down on whether you're testing entanglement
Yes.
between 2 things, and
Yeah.
or you're setting some single system measure of quantumness.
Exactly,
This could
yes.
be coherence
It's
or anything
exactly,
else.
this is-
I mean,
so
it
this
happens
is-
to be the negativity because this is a
Yes.
Gaussian.
So exactly, you could
the
also
continuous.
use coherence potentially in this test. Yes, I mean,
So I think the
it's-
correct thing to say is that both phenomena is self-interacting, gravitational self-interacting matter.
yes,
Because
it's
probably that have to be
Question, or you had
something
another
to do
one?
with the Planck mass
Yeah, I
scale.
had another one.
But it's 2
I
different
don't
phenomena.
mind if you had one.
Yes, yeah. I think the thing is that you can't have entanglements between these atoms in the BC, and that's why I talk about it as being a single party system.
It's probably easy to control somehow.
Maybe.
But I mean, yeah.
Yes.
I understand.
There was the other question from Marta, and then we should just.
Yeah, well, actually, my question was more of I didn't really quite understand the mechanism that you use to eliminate electromagnetic interactions, self-interactions in the
yes.
system. So how does that actually work?
Well, yes. Problem is, I've tried hard to look for a sort of neat way of understanding this in a physical context, and I haven't been able to find it anywhere. So it seems the way in which people describe it in BCs is quite complicated. So it involves I don't want to be too long. So it involves basically, in this interaction, you have what they call open channels and closed channels. And the open channel involves a scattering between these atoms, which is allowed by energy conservation. And a closed channel is one that's not allowed by energy conservation. And your closed channel can be a bound state, which is not allowed by energy conservation. And both can have different magnetic monopoles. And by using this external magnetic field, you can interact these open and closed channels, and then that leads to this Fishback resonances. So it's not just in BCs, it's also in nuclear physics and cold atoms as well. And it's this. So I'm afraid I don't have a very good sort of way of intuitively describing it, but that's the textbook way that they write, is that this interaction that creates the Fishback resonance.
Okay, sorry, now we're limiting ourselves to 2 questions. So let's thank Richard.